generic and so complex in just 1 hour. So what we plan to propose is to present some guidelines and actually, so we'll be talking of the mesh for CFD. It's not for structural engineering, it's CFD. And here are the few elements that I'm going to mention in the presentation. And you should know that the context is, as presented, I told you, Christophe, I've been working in turbo machinery CFD, and in particular in the hydro turbines. And I've been working for NumIbérica mainly. I've used also some other software, but mainly NumIbérica. So I'm going to talk about NumIbérica technology. And at the end of the presentation, Daniel will do a demo of our last version of our Omni software and of the two mesh generators, AutoGrid and Express. Okay, so as you know, if you want to have a good simulation, the first thing is to have a good mesh. Okay, you know, the garbage in, garbage out. Also say low quality mesh, low quality simulation. And we have this sentence at NumIbérica. We say mesh is a key. So it's and I think it's quite true. In the whole experience of at NumIbérica, myself and colleagues, really we most of the time we focus on the mesh as really the main step to get a good simulation. So one of the main issue when you start will be the geometry. So you will start with a geometry that can be in a CAD, coming from a CAD system, such as CATIA, etc., ProE, etc., which is actually continuous. So you have continuity of the geometry, or you can get something that will be defined by triangles, and the STL for stereolithography, or similar if you have image and so on. And so basically we will have these two kinds of geometry input. For structural mesh, usually you will work with CAD, while for unstructured, you will use STL geometry files. And when you start from CAD, you enter in unstructured mesh software, you have to triangulate your geometry. So you get the geometry, it depends where it comes from, but it might need some defeaturing or cleaning because maybe you have too much elements, and sometimes you get the CAD from other companies, and there are some other constraints or objectives when they do the CAD. So you get the CAD, you have to remove some elements, maybe you have to close some volumes. So all this it is sometimes also included in the software system, in the mesh generation, and in the mesh generation. So you have you will need to work with a CAD cleaning software, holes closer, and in our case we have also a tolerant mesh generator to unclean CAD, which is the Omnis Express we will show later. This is the kind of thing you have to do. For example, you have to cap holes, to add some surface to close the volume. You have to create or remove fillets depending on what you fast. You maybe need to do some Boolean operation to get the volume you want to mesh. And also you can have to extrude some face. Well, and these are some basic CAD manipulation that if you don't have a CAD system, it's better to have it directly in the mesh generation tool. So this is in the case of triangulation. So you will get a geometry that is continuous, and you convert it to STL geometry, and you can have different level of tessellation. There are a few parameters you have to define, and something I want to show here, which is an issue we have quite often in the mesh generation, is that you can have a geometry which is conformal. It means that locally, if you have two surfaces, they have a common edge, and all the vertices of the triangles will be at the same place. Otherwise, you can have geometry they share an edge, so from a continuous point of view, the same. But then, if you look at the STL discretization, it will have different place. So, some place you can have an edge where you can have a point. It can be on one surface or another, and not on both. So this is the kind of problem we can face, and this is what also your software system might probably need to retriangulate and to improve the triangulation, avoid some noise you can have at the definition, and or do a conformization of the geometry, such as the teaching here we can see, where these two surfaces share the same, exactly the same nodes from the geometry at the boundary. Another operation you might have to do is to close some holes. So here we have, for example, a tool that is AutoSeal, where it uses some mesh generation techniques to define some surfaces. This is triangulate surfaces to close the hole where we don't want to have a mesh. So you have different parameters to define that. I'm not going to enter more into this. It's just to mention it to you. Okay, so you probably already know that there are mainly two kinds of mesh. You have the structural mesh or unstructured mesh. So the structural mesh is often called as a block structural mesh. So you define different blocks that you put inside your geometry to fit the volume, to fill the volume. And normally when you have that, when you use this technique, this type of mesh is mostly for quite of simple geometry, is where you can quite easily define this. Otherwise, if you want to go to more complex geometry, you need very specific mesh generation tools that are automated with template scripts for a specific application. This is the case you will see with AutoGrid for turbo machinery. Structural mesh are very fast to generate. You have different blocks, and the blocks, the inside structural is fast to generate. It is good to use, easy to align your cells with the boundaries. So this is very good for the viscous layer mesh, and because you can generate easily an anisotropic mesh. You get cells that are only X, and I don't know any CFD solvers that cannot work with that. I mean, it's compatible with nearly all CFD solvers. Now, when you work with unstructured mesh, you can use really any kind of geometry. You can really have very, very complex geometry. This is an example of underhood here. But on the contrary, you need probably a parallel mesh generation, because you often end up with a large amount of cells, much more than structured. It's a technique that is more flexible for when you have very different geometry size. If you have a very small elements you want to capture and in a very big environment, for example. It is also easy to, well, relatively easy to implement after that some grid refinement or other set methods. And but then you will have different element types, and this is you will have to check which kind of solver you use, because sometimes it's not everything is not compatible with any solvers. Which that a bit mainly the issue is the conformal or non-conformal grids. If we use only nodes or not, we will see that later on. So when I started working at NumIbérica 20 years ago, we all had this KIM printed and right at close to our screen. So we are checking all the time how to define our blocks, what phase number, what age number, how to define the segment, and so on. And you have to define all these blocks in your geometry. At that time, there was nearly no unstructured mesh, so we were only working with structural mesh. And you have to define all this. So this now, you will not have to do it anymore. I mean, normally, unless you develop a structured mesh generator, which is very unlikely you will not do, you don't have to work with that. This is things for the past, but it's still inside the mesh generation systems such as IgG, for example, from NumIbérica, which is block structural mesh. For structural mesh, when you look at the grid quality, as the cells quality, we mainly look at three elements. One is orthogonality. This is we want to have cells that are close to cubes, so orthogonality of about 90 degrees at the edge. Then we would look at the aspect ratio, which is the stretching of the cell. How flat is the cell? So you will have high stretched cells in the boundary layers, when here you have aspect ratio of 1, actually. And then we look at the expansion ratio, which is also quite important. It's the ratio of the cell size of two consecutive cell size in the different direction. And this, we want to respect these values here. Let's say min above 20, max aspect ratio under 500. This is a bit code dependent, and max expansion ratio under 2. And actually, in the boundary area, we try to be close to 1.2. So this is an example of structured mesh software. We have it's a commercial one. It's IgG from NumIbérica. There are some others from the competition, and maybe there are some free mesh generator as well. And all this, it's a bit more simple than what I've shown before, because you have some development that have been done. So you can interactively do the blocking. You have some tools to do the blocking in an automatic way, for example, butterfly topology. But still, if you go to a complex geometry, sometimes it will be very hard to do all these blockings. So this is why, for example, for turbo machinery geometry, turbo machinery case, NumIbérica has developed what is called autogrid. So this, in a way, we managed to have all the blocking topology and so on done in background by the software, and you just have to give your input as a user, and like what kind of cell size you want, where do you want the cell size, where do you want more cells, etc. So this is actually one of the cutting edge software for turbo machinery. It is used by all the major industries. So if you will be dealing with turbo machinery CFD in the future, you probably will hear about Autogrid 5. These are some examples of mesh we have in the hydro industry. This is from a workshop from the Norwegian University in Trondheim. We had a workshop, and we proposed with some people from Quebec. We made a group, and we proposed a mesh, and we use Autogrid 5 to produce the best mesh possible. And you can see here we have really mesh following the blades, so the flow will be aligned with the cells, which is very positive for the pace of your solver and the accuracy of it. You have refinement close to the walls. Here, this is a refinement for the sea leakage flow in trends. You can see that this topology, all this is automatically defined, unfortunately, for the user. So you just have to define the number of points you want, and the viscous layer mesh with the first cell size, and then the topology adapts itself to all kinds of openings. For example, here we have 3 different openings of the guide. Another example of this automatic blocking tool here is for the sea leakage flow, because we also call it labyrinth, and so we generate automatically a block structure. Okay, but this can be done because it is quite, let's say, simple geometry. It's 2D, and actually we always have the same kind of geometrical structure. So we can define here the blocks in an automatic way. And then you see then at the end we generate 3D. This is an axisymmetric mesh, and can this way simulate the flow in the sea leakage. So here in this slide, I try to summarize all what comes up when you do a mesh, a structural mesh. Well, first you have the geometry in CAD format, and you have to be very careful with the geometry and what and how it comes. If it needs some cleaning, it usually needs to be very clean. And then you should know, unless it's automated, we have to define a mesh topology, which is the block structure and the shape of the blocks inside your volume. Then you will work with green refinement in order to capture the geometry, all the needed geometry, and where you expect to have some flow gradients. It will also depend on the simulation requirements. If you do steady, unsteady, harmonic, FSI. And then you will have to define your viscous layer mesh. You probably know this from the Blasius equation, and where you have different layers, and depending where you put your first point, what kind of turbulence model you can use with wall function or not, extended wall function, and so on. And so this and directly translate in the mesh and the viscous layer mesh. So if you want, for example, normally work with the I+1 with low Reynolds mesh. And so this is a kind of mesh you would put very, very close to the walls. If you start with, if you're going to work with wall functions and simulation with a turbulence model with wall function, then you can have Y plus of let's say 30-50. So this translates in a very in a coarser mesh close to the boundary layer and less cells. And then one thing that will be important as well, what resources you have for the computation and what your the deadlines of your projects. And so you might have to do some choices in the type of mesh you do, in the viscous layer mesh, or what you capture or not. So I'm going to move to unstructure. We have this slide on NumIbérica trying to summarize a bit the difference between the different kind of grids. Okay, this can be discussed, but what we say is that the best quality and the lowest cell count is usually for the structured grids. Then you go to unstructured but full X grids, and then you have X dominant, and then you have tetrahedral grids, but that we don't have actually at NumIbérica. And the difference here is mainly if you have a conformal or not conformal geometry. If you have a geometry with some defects, it is not clean. Otherwise, if you have a clean geometry, you can go to full X. So different concepts in the mesh generation and structure. So we work with volume to surface. There are other techniques that are surface to volume, but NumIbérica is volume to surface. And so you first generate an initial mesh, which is just a Cartesian mesh, subdivision of your volume. Then at the next step, you have the adaptation, where you will capture different geometry features with refinement. Either you want a cell size, or you want to adapt in function of the curvature, or if you have a gap and you want a number of cells in the gap. Then you have also the trimming step, where you remove the cells that are off the volume that you're interested in. And then comes all the code, that is the snapping optimization. Snapping is the projection on the surface edge to capture edge vertex, and you have to insert buffers, you have to regularize your mesh. So this is really a kind of solver actually. In this part, you also have optimization of your mesh, a 3D optimization. And then after that, the last step is to insert the viscous layer, where you have different techniques actually, and you can also have another optimization step after that. Here we have different grid quality criterions. First, we want to avoid negative cells, twist, concave cells. Concave cells, for example, the cell is entering, this point here is entering the cell. And we'll be looking at different values or parameters, but this is very solver dependent. You don't have the same if you're using NumIbérica, if you're using Fluent, if you're using OpenFOAM. You can have different value and things to expect. And actually, in our mesh generator, we have specific mesh optimization algorithms depending on the solver you're going to use. At NumIbérica, we'll be mainly looking at maxi equiangular skewness. We try to have it between lower than 0.95. Okay, this is an example of hydraulic mesh for hydro turbines with typically the spiral casing with the stay vanes. You must also have the guide vanes. In this case, we have an X-dominant mesh. You can see you have some prism. And normally X-dominant, it means that you have above 60–70% X, and all other components can be prism and tetra, for example. This is another example of a mesh. In this case, we also have the guide vane. You can see that this will be terrible to try to mesh with a block structure. You have it's a very sharp angle. It's a spiral casing, so it's like if you want to mesh, you have a structure that is going at itself. It's the snake that is hitting its tail. So this is very, very difficult, and typically we use this unstructured mesh for this configuration. Some of the difficulties we face when we generate a mesh, it can be very sharp corners. You see, if you don't have very specific development, this is the kind of thing that can happen to you. Then we try to capture some narrow gaps. So this is also, you start from a kind of isotropic mesh and you want it anisotropic, so you want to stretch the cell in a direction. So you have to define some very specific algorithm for that. Then another difficulty is a viscous layer, or you define the viscous layer. So here you have different examples of viscous layer technique. One is the inflation, so you just push all the cells and you insert your viscous layer. Then you have extrusion where you cut all the cells, install the viscous layer, and then you have a transition layer of that and deformation. That will be something in between, closer to the inflation, but in between. And so this really also depends on your application. For example, for aeronautics, they will be mostly with extrusion. They want very big viscous layer of 40–50 cells. And very, very regular viscous layer. And this becomes difficult at different location of the plane. And for hydro turbines, we probably work mostly with inflation, with more robust and sufficient for our needs. And all this implemented in Express Hybrid, and you can combine it as well. Another challenging configuration now, it's what we call the scene walls or the multi-fluid or multi-domain. In this case, you have two fluids. You have a coolant, you have air, and in between you have a pipe. And you want all this to be matching. And so you have to have some cells on the grid point must be on the scene wall, which is just a surface. And the next steps we don't see here is that we also want boundary layer mesh, viscous layer mesh for the fluid part, but not for the solid. Okay, then something we promote and actually I'm personally very favorable to that is to combine structure and unstructured. So use structure as much as possible, and what is to compress, you go to unstructured. And then, so you have a non-matching connection in between. And at this non-matching, you can define, you should try to have the same cell size. So you will have specific algorithms, non-matching, full non-matching, GGI in CFX, for example. And you can define a cell distribution to make sure to have the lower error at this interface. And here you can see it's a full X mesh for the stay vane here. And you see it's non-conformal because you have hanging nodes. Hanging nodes is here, if on the pointer, it's when you have one cell's face that is connected to various ones. And so you have this point here is called hanging nodes. This is another example of a combination of structure and structure. So you define a structural mesh with autogrid for the blade. So you have a mesh that follows really well the blade surface, and just where you have something where you cannot define a structural mesh, or it's really too complex, you remove a part of your structural mesh and you insert an unstructured part, and in this area, then you generate your unstructured mesh. And also, again, you do your best to ensure continuity of the cell size as the interface. Okay, as before, so this time, what comes up when you generate an unstructured mesh? First of all, okay, you would have your geometry in STL, and we have seen the different issues before. So you might need to clean, you might need to close some holes, you might need to conformalize. Depending of that, you will have some requirements for the mesh you will generate, for the kind of mesh you will generate, depending on the geometric quality and what's in it. Then you will define your refinement, your adaptation on surface and volume, and Daniel is going to show you that. To capture the geometry, to refine where you expect some for gradients. It's also dependent of your simulation, so what you are going to do. Then again, we have the viscous layer mesh, and still important to depend what are your resources and project deadline. So you might have to change your simulation and what you want to do. One thing that often comes up as well is you want to know the grid influence, and maybe your project leader or your customer wants to know, have you done a grid convergence study? So the first thing is, I think it's important to check the grid influence, but the grid convergence study, it's not so easy to do. It's not just to check the results of your simulation in function of the grids of the number of cells, and this is an example here where we have a first mesh here, which is a high Reynolds mesh, which is already good to be used with well function for a turbulence model with well function, and okay, and a first different mesh is just to change the boundary mesh to be able to use a low Reynolds turbulence model to go to a y plus value of 1 or something like that. So you just increase a bit the number of cells, but in this case you can have some huge, very important change of the prediction or of the simulation results. And then you can increase the number of cells. And for example, here we double the number of cells, which is quite important. But actually, if you look at the mesh, we have just increased it by 25% in every direction, and for the flow, the expected change is very small. So this is a difficult topic, not easy, but yes, I agree, we should check always the grid influence in a way or another. Another topic which is very interesting now is what is the adaptation. Here you can see we don't have that for turbo machinery, actually. It's not something I have seen nearly... So, but we have it, for example, for our fine mining program for naval application, where we need to capture the free surface. So you will have mesh that adapt to the free surface, and here we have the mesh also that adapt to some secondary flows. Okay, and so in this case, we use it for unstructured mesh. Another example is here. And in this case, we also have another method which is called the overset. The overset is you define two different mesh, and one of the mesh is moving inside the other one, and so you transform the information from one mesh to another. And in this case, what we do also in our solver, in our software fine mining, is to have this overset mesh, and together we get adaptation so that we ensure the continuity of the cell size in the very overset boundaries. Okay, so I'm close to finish for my part, and I will go to then for Daniel. So just some comments from our experience. So the choice of the type of mesh you do and the characteristics of the mesh. So they're related to the physics of the problem, the geometry, and the numerical method used in the simulation. One important thing is always to check and control the geometry definition. I mean, I've been giving support for 20 years to many customers, and maybe half of the problems of the quality of the simulation are at this stage. The geometry you put in is really important to control, so that you know that the mesh will directly depend on the quality of the geometry you enter, and if it's not of quality, you should know that you cannot get something good where it is not well defined. Our proposal is to use structural mesh as much as possible, and then combine with unstructural mesh. So this is directly for the efficiency of your whole simulation process. As we just said, just check your mesh inference in a way or another, and if you can, adapt your mesh manually or not in function of a convergent flow solution. Because I say convergent here, because if your flow is not convergent, you might adapt to something that is transient and during the when the simulation is starting to converge, and so it's not good to do the adaptation at this step, because you can change the solution or adapt to something that is not real. And then another recommendation is to work with experts in your application. I mean, if you work with commercial software or other kind of software, work with the technical support. Try to get good technical support, so from experienced people, and that can help you in defining the best mesh for your application. So just before the demo, to mention you that at NumIbérica they have some specific solution for academia. There is a free student offer that you can check here for the students. For the teachers and researchers, we have some classroom license and some R&D license. And then we also do some sponsoring. So if you have an interesting project at your university you want to see with NumIbérica, if you can collaborate, NumIbérica is very open to that. And here you have our emails if you want to contact us. I think that ends my presentation, and now Daniel is going to do a demonstration of our software on this.
Thank you, Rémi. I'm going to